All right, now in this problem, we're actually going to solve for the empirical formula from the data coming from a combustion analysis experiment. And I've mentioned this before in class, and it's also in one of the mini lectures, sort of explaining what combustion analysis is. But the only thing you really need to understand right now to be able to solve these problems is that in combustion analysis, we're going to put some amount of an unknown compound, and usually we have an idea of like the elements that are in the unknown compound. So for this one, we know that there's hydrogen, carbon, and nitrogen, but we don't know what the relative ratios of those elements are in the compound. So, we're trying to find that empirical formula, that whole number, simplest whole number ratio between the elements, knowing what the elements are, but just not how many of them we have per mole. So if we take this amount of mass of the compound and we run it through combustion analysis, what's going to happen is it's going to react this compound with oxygen to form CO2 and water, which are the two main products that we get. And for this particular experiment, it's also pointing out that there's some nitrogen and oxygen containing compound that's also going to be formed. But we're not going to focus too much on this point right here because that is not something we're given data regarding. We're just kind of told that, hey, the nitrogen is going to form this nitrogen oxide compound, but we're not told any sort of information about it, so we can kind of ignore that point for now. What we do pay attention to, though, is the amount of water that's being formed and the amount of carbon dioxide that's being formed. And one of the first things that always confuses people is that the amount of water, right? We've got this 0.1676 grams of water plus the amount of CO2, carbon dioxide, that are being formed in this process. If we add those two values together, we get 0.3314 grams total of these products. And I'm only pointing this out because people get confused on this and they go, wait a second, how can we have 0.3314 grams of stuff being produced when we only started with 0.1156 grams? And the key to that is to remember that this oxygen is also being added in to this reaction. So the oxygen in the water and the oxygen in the CO2, note that in this case, those aren't even coming from the original compound because we don't have any oxygen in our original compound. We've only got hydrogen, carbon, and nitrogen. And so that additional oxygen that's being added in is adding some mass. And so that's why it almost seems at first like we're disobeying the law of conservation of mass. But we can't forget about that oxygen that's being added in. So I hope that clears up one misconception that a lot of people will have on problems like this, where they'll get kind of thrown off by all these mass arguments. I'm going to clean this up a little bit and actually get into solving this problem at this point. And we want to go back to this concept of the fact that this water and this CO2 are being formed from our original compound. So that means that all of the hydrogen in the water and all of the carbon in the CO2 had to come from the original compound. So these masses that were shown here are going to allow us to figure out what mass of hydrogen was in the original compound and what mass of carbon was in the original compound. So that's where we're starting with this problem. Now, in order to accomplish this, we're going to utilize the mass percent, because this question of, me prompting this question of how much hydrogen is in this water that would have come from the original compound and how much carbon is in this CO2 that would have come from the original compound. And if we know how much of this water and how much of this CO2 we have, and we know the formulas, then we should recognize that this is just a simple case of using the mass percent to figure out the mass of an element inside a certain mass of a compound, where the certain mass of the compound that we're starting with are these products that we formed from the combustion analysis. So the 0.1638 grams of CO2 and the 0.1676 grams of water. And we're going to try to figure out what portion of each of these masses is due to carbon for the CO2 and what portion is due to hydrogen. Now, I could solve for the actual mass percent of hydrogen and water and the mass percent of carbon and CO2, get those percentages, and then, treat this like okay, I'm taking the percent of a mass. And if that's more comfortable for you, then I understand that. But I really encourage you to recognize that we can also do this all at once without actually solving for mass percent at any point by just using the mass percent expression as a conversion factor. So mass percent, remember again, is the mass of a component over the mass of the total. And so the total mass is going to be the CO2's molar mass, which I've solved for previously by just adding up the molar mass of carbon and of 2 oxygens. And then I've got 1 carbon in this molecule, so I want the molar mass of carbon on the top as the component for this mass percent expression. And you'll notice here my units for grams of CO2 are going to cancel out, leaving me with grams of carbon. So this amount here is the amount of grams of carbon in that CO2, and it's also the amount of carbon that comes from the original compound. So it was in this original 0.1156 grams of the compound. Same thing with the water, except to be really careful here to remember that there's 2 hydrogens in water. So for the mass of the component, we need to take the molar mass of hydrogen and multiply it by 2. And then, of course, we have our molar mass of water on the bottom. So mass of the component over the mass of the total. And then, again, we're not solving for the percent at any point here. We're just using that setup of the mass percent as a conversion factor so that we're now getting that there's 0.01876 grams of hydrogen in the water that's formed. And since all of that came from the original compound, this is the amount of hydrogen that was in the 0.1156 grams of our original compound. Now, to solve for the amount of nitrogen in the original compound, when we get down to just 1 element being left, this is why we don't have to worry about, this N oxide, this nitrogen oxide thing that's being formed, because once we know how much carbon and hydrogen are in the original compound, it's easy to solve for the amount of nitrogen in that original compound by just subtracting the masses from the overall compound mass. So notice that's what I'm doing here for nitrogen. I'm starting with the 0.1156 grams of the compound, and I'm subtracting out the masses of carbon and hydrogen that I've now determined from here, right? These are going in over here. And what I'm left with should be the mass of the compound that's due to nitrogen, because that's the only other element that is contributing mass to this compound. So if our goal is to get the empirical formula in this first part, remember that in order to solve for an empirical formula, you need to know the number of moles of each element that are in a certain amount of the compound. And we can easily get to moles from grams. So the only thing we want to check here is that the grams amounts that we've got listed here now, this grams of carbon, grams of hydrogen, and grams of nitrogen, that they are all coming from the same amount of compound. And with the way we solve this, we know that they are, because these CO2 and water measurements both came from the 0.1156 grams of compound being combusted. So again, we know this grams of carbon and grams of hydrogen, that's the amounts in the 0.1156 grams of compound. And we use that information to solve for the grams of nitrogen in this amount of compound, the same amount of compound. So since all those masses come from the same initial amount of the overall compound, all we need to do is convert those masses into moles. So converting those into moles is as simple as just taking the mass amounts that we have from this previous part and dividing each by the molar mass of that element. So for carbon, we're dividing by 12.01 grams. For hydrogen, we're dividing by about 1.01 grams. And for nitrogen, we're dividing by about 14.01 grams. And so we're getting basically just this simple conversion again of going from grams to mole, which is essentially just dividing by the molar mass, to get each of these values into moles. And so again, these moles that I have now all tie back to the same amount, original amount of the compound. These are the number of moles of each element in 0.1156 grams of the compound. So then from here, we want to now look at the ratio of these moles. And if you remember, the way we want to compare them is you should always find the number of moles that is smallest, and you're going to use that value to compare to all the other elements, and you're going to divide by that value. You're going to divide by the smallest number. Now, in this particular case, we've actually got the same number of moles of carbon and nitrogen, so it doesn't matter which one of those you choose. I just decided to use nitrogen for this, And I did go ahead, I mean, most of you probably wouldn't bother to write this out if you notice that the moles are the same, but let's just recognize here that if I divide the moles of carbon by the moles of nitrogen, I'm going to get a value that's pretty much equal to 1. And let's remember how to interpret this. This 1 is interpreted as this is 1 mole of carbon for every 1 mole of nitrogen, right? Because that's the way I compared those two. That's what that 1 means. Now, in terms of the hydrogen, if I divide the hydrogen by the number of moles of nitrogen, I'm getting 5. And so again, remember, this means 5 moles of hydrogen per every 1 mole of nitrogen because of the way that I've defined that. So these mole ratio comparisons are actually giving us our subscripts for the empirical formula. We know now that the thing we divide by will pretty much always be a subscript of 1, because you'll notice when we divide by the moles of nitrogen, we're always getting this per 1 mole of nitrogen. So in my formula down here that I've put in, notice that I have 1 nitrogen. Notice that the moles of carbon, we also have just 1. So for carbon down here, I have just 1 carbon. And then for the hydrogen, since I have 5 moles of hydrogen per mole of nitrogen, that means that I'm putting a 5 as my subscript in the empirical formula. Now again, if you don't know the order of how to put the elements, that is okay at this point. It's okay if you jumble these around a little bit, but typically it goes carbon, hydrogen, and then other elements. So that is why I've started with carbon and hydrogen here. Now once we have the empirical formula, we can move on to this next question that is now telling us the molar mass of the compound and asking what's the molecular formula. So this is this process now of comparing the empirical formula's mass to what the molar mass of the compound is and seeing whether or not we have a molecular formula that's a whole number multiple of the empirical formula. And in order to do this, we need to start by solving for the empirical formula's mass, or the empirical mass. So solving for the empirical mass is the same as solving for a molar mass. We're just using the empirical formula and we're adding up the masses of all the elements. So if there's 1 carbon, we have the molar mass of carbon. If there's 1 nitrogen, we have the molar mass of nitrogen. And if there's 5 hydrogens, we'd have 5 times the molar mass of hydrogen. And we add this all up and we get our empirical formula mass. And then we compare the molar mass that we're given to the empirical mass that we just solved for to see if they're a whole number multiple. And we always put the molar mass on top and the empirical mass on the bottom. And if you notice, in this particular case, we're getting a ratio of about 1, which means that the empirical formula is the molecular formula. So this can happen, and I've mentioned previously that you always want to make sure when you're comparing the molar mass and the empirical mass that your empirical mass is either equal to or less than the molar mass, because if it's not, then you probably did something wrong. But this is a classic example of a case where we actually have an empirical mass that's pretty much exactly the same as the molar mass. And that can only be the case if the empirical formula represents the actual molecular formula of the compound. So this is just one of those situations where this compound happens to have a formula that is the simplest whole number ratio of all the elements. And there's a bunch of other molecular formulas out there that are also like this, where they just happen to be the simplest whole number ratio between the elements. So watch out for this sort of a thing to happen. Now, if we had compared these and the number we got was 2 or 3 or something like that, then remember that going from the empirical formula to the molecular formula usually just involves multiplying by some whole number ratio. In this case, we're multiplying by 1, so nothing changes, right? So the two formulas are exactly the same.